Section 4.3, Logarithmic Functions. So to begin, in the most general sense, a logarithmic equation is the mathematical opposite of an exponential equation. Now, why is that so important? Well, if I'm ever asked for an inverse of, say, 2 to the x, how did I find that? Well, we know we interchange our x's and y's, so I have x equals 2 to the y power. But how do I get that y down so I can solve? Well, there's a special equation for the mathematical opposite of an exponential. That's logarithmic. So let's go over their definition. A logarithm base b a positive number x satisfies the following equation. For x greater than 0, meaning your x has to be positive, and b greater than 0, and not equaling 1. So y equals log base b of x is equivalent to b raised to the y equals x. This is so important. Write it in a post-it, have it handy, write it on your hand. This is so important, and it'll be important for the remainder of the chapter. Now some points to make note of, where we read as log b of x as logarithm with base b of x, or log base b of x. The logarithm y is the exponent to which b must be raised to get x. Also, since the logarithm and exponential functions switch the x and y variables, the domain and range of exponential functions are interchanged for logarithm functions. Therefore, our domain is from 0 to infinity, and our range is all real numbers. So there's some homework problems about domain and range. That's worth noting. Okay, once again, one of the most important helpful things to remember for this section is how to go from logarithm form to exponential form and back. So we see this problem here, this image, and we see that to go from logarithm to exponential, we take our base, we raise it to the y power equals x, so that we have b to the y equals x. And we can also use that to go to logarithm form. So your base stays the same. So we have log base b of a equals c, like we have here. And it's so important. There'll be a lot of questions in your homework where you're simply asked to go back and forth. And we have a lot of examples in our notes to help us learn how to go from back and forth. So first example says, write the following logarithmic equation as an exponential form. Okay, so the base is what I keep an eye out first because your base stays the same. So I have a base of 6. Now I need an exponent and something that it's equal to. We have them here. And the way I think about it is that they're switched. So my exponent is 1/2, and my answer is square root of 6. That's our answer. So I have 6 to the 1/2 power is square root of 6. And yes, that is true, right? The square root is like a radical, a rational exponent. Let's take a look at this next problem. So the way I think about it is my base is the same. I have a base of 3. Now it's a matter of just finding out what my exponent is and what it's equal to. The way I think about it is we switch that order. So 3, not 3, so 2 and 9. And isn't 3 squared 9? Yeah, so our answer is 3 squared equals 9. There we have it. It's not so bad if we think of it that way, right? Let's do another example. Write the following exponential equations in logarithmic form. Okay, same thought. We have our base. So I have log with base. Okay, now I'm going to swap my order so that I have 8 equals 3. My answer is log base 2 of 8 is equal to 3. Next example. Your base stays the same. Now I need to I need to write that smaller. Okay, so my base is the same. I need to find an argument for that log and what it's equal to. And we have those numbers. It's that 2 and that 5. Now 2 comes first, so I switch the order so that it comes last. 525 comes last, so I switch the order so it comes first. So our answer is log base 5 of 25 is equal to 2. 10 to the negative 4 power equals 1 over 10,000. So I think about it the same way. We have a base, so I have log base 10, and then my order is swapped, so that I have 1 over 10,000 equals negative 4. My answer, and you need to write it twice. I don't know why I'm doing this. I just wrote it twice for you. So that, I don't know. It's still the same answer. And when you think about it this way, it's not so bad. I know it's different. And when I teach college algebra, it's a big concept, but you learn so much in college algebra. Depends whether you've spent enough time on this. Hopefully, since you're seeing this second time around, it makes a bit more sense. If not, email me. I'll be happy to help. Example 3. Solve y equals log base 4 of 64 without using a calculator. I don't know what we're doing, right? It seems like a big idea to take in. Logarithms are weird, but we're much more comfortable with exponents. So what did we do? Change to exponential notation. So that we have our base is 4, so I have 4 raised to the y power equals 64. Okay, y raised to what power gives me 64? Well, isn't y to the third power 64? I'm sorry, 3. Isn't 4 raised to the third power 64? 4 times 4 times 4, 64? Well, 4 times 4 is 16, and 16 times 4, 64. Yeah. So I'm going to steal this exponent because I know that exponent of y should be 3. So my answer, y is equal to 3. Because isn't that what we wanted to find, that y? But once we wrote it in exponential form, we were able to see what all of this meant. So this question mark is now solved. We know what we were seeing. Next example, evaluate without using a calculator. Well, we're going to follow that same idea. Logarithms look a bit more intimidating than what they are. So let's go ahead and write in exponential form. My base is 3, so I have 3 raised to the, and I remember you switched your order. So I have y raised to the, or 3 to the y equals 1 over 27. Now it doesn't seem like we switched the order here, but we have 3 next to the 127. You would think the 127 goes next to the 3, but you swapped the order there. That's what I meant by swap the order. Okay, so I have a fraction. Do you remember how to make a fraction from exponents? Yeah, you know that you need a negative exponent. So if I'm making a fraction, resulting in a fraction, then I for sure need to have a negative in my exponent. Now, 3 times what gives me, 3 raised to what power gives me 27? 3 to the third power gives me 27. 3 times 3 is 9, times 3 is 27. So 3 to the negative 3 will give me 1 over 27. So negative 3. My y is negative 3. Moving forward, using common logarithms. Sometimes we see logarithms written without a base. In this case, we assume that the base is 10. In other words, the expression log 10 means log base 10 of x. This is called the common log. So what we should notice is, where is that base? I don't have one. If you ever do not see a base, you assume it's a 10, unless there's another base there. A common logarithm is a logarithm with base 10. We write log base 10 of x simply as log of x. The common logarithm of a positive number x satisfies the following definition. For x greater than 0, meaning x is positive, y equals log of x is equivalent to 10 to the y power equals x. We read log of x as a logarithm of base 10 of x, or just log base 10 of x. The logarithm y is the exponent to which 10 must be raised to get x. Okay, so let's evaluate without using a calculator. Logarithms, they always throw me off. And again, if we don't see what's going on, you can write it in exponential form. So we assume a 10. 10 to what power gives me 1000? Okay, a trick I learned when I was younger is your zeros tell you how many exponents you have, or what your exponent should be. So if I have 10 to the third power, that is 1000. So my y is equal to 3. Now the punchline of this example is you did not have a base. So how were you able to write an exponential form if you didn't have a base? You have to go, aha, my base is 10. That's the big deal for this problem. We didn't have a base, so we assume a base 10. Now we need to talk about calculators. Calculators should be your best friend. Even if you're not allowed to use them, they're super helpful and it's worth your effort to know how to use them. And logs are an example of that. There are some logarithms that we cannot solve by rewriting in an exponential form. So for such problems, we have to use a calculator, such as this example. Evaluate or find y equals log of 321 in 4 decimal places using a calculator. If I take the time to write it in exponential form, there's no such 10 base to an exponent that gives me 321. So I need to use a calculator. So take your calculator. If you don't have one handy, you can use your phone. If you turn it sideways, it opens up more options and you have more buttons to press. So play with it until you get 2.5067. You take the logarithm of 321. Now, it depends what kind of calculator you have and what you're using. Some are, I read a textbook that's talking about calculators and it calls them like innies and outies or something like that. So order matters and depends on how your calculator works. So some calculators make you type in log and you punch in your number and you have to close your parentheses and you get an answer. Other calculators make you type in the number and then you press the log command so that you can get the applied log. So that's what I mean by innies and outies. It depends what your order is. However, play with it until you get the right answer, which is 2.5065. Now, just like common logarithms, there's natural logarithms. The most frequently used base for a logarithm is e. Base e logarithms are called the natural logarithm. The base e logarithm, log base e of x, has its own notation, ln. And when I write it using homework or notes, I always do a cursive L and an N, so I don't confuse it with a 1, because I will probably confuse it with a number. Just a hint. Most values of ln can be found only using a calculator. Take a moment to inspect your calculator and find the natural logarithm command. So it's usually Sometimes you'll have a ln and a x, and that's a button. For other buttons, it's usually found with the e to the x, and maybe the ln is in the shift option. So to get to those colored buttons in your calculator, you might have to press the shift command first. So take a look at your calculator and see where ln is found. Definition of natural logarithm. A natural logarithm is a logarithm of base e. We write log base e of x simply as ln of x. The natural logarithm of a positive number x satisfies the following definition. For x greater than 0, y is equal to ln of x is equivalent to e raised to the y power equals x. We read ln of x as a logarithm with base e of x, or the natural logarithm of x. The logarithm y is the exponent to which e must be raised to get x. Since the functions y equals e and y equals ln of x are inverse functions, ln of e to the x equals x. So ln and e are like mathematical opposites, so you're just left with the x. For all x and e equals x, for x greater than 0. So instead of writing log base e of x, we can just write ln of x, and that's how we interpret it. Now ln is the inverse of e, and so if we're left in a situation where we take the ln of e, we get the exponent in return. All right, that's all for section 4.3, logarithmic functions. Your homework is numbers 5 through 51, every other odd. Thank you.